Alright guys, I think this is the point in our course which everybody's waiting for, the tunneling phenomena in quantum mechanics, how a particle can tunnel through a potential barrier. We're gonna go back to the problem of the potential barrier, but this time we will consider the case where the energy of the particle is less than the potential V0, and let's see what we get. Alright, I've sketched out the potential like here. It stays the same. I left out the definition because you should be familiar with it already. But anyways, if you want to know, is that from x between 0 to a, the potential is V0. And from x less than 0 and x greater than a, the potential is equals to 0. So we have also discussed that classical mechanics tells us that we have a particle over here, we have a certain momentum, and then as it reaches this region from x between 0 to a, the momentum would decrease, and then as it comes out of this area over here, the momentum would increase. And then previously, when we had the energy of the particle greater than the potential V0, quantum mechanics tells us that now the particle is able to reflect. But now we're considering the case where the energy is less than the potential V0, and we see that the picture changes altogether. So classical mechanics, this time the particle will not go through this region over here. Instead, there'll be total reflection because the particle cannot have negative kinetic energy as it enters the potential barrier. But we'll soon find out that quantum mechanics predictions tells us a totally different story. That is the point of our study today. By analyzing using quantum mechanics, what does this problem tell us? Okay, the solutions to the Schrödinger equation in the three regions, which is here, here, and here, I've already written it out, okay? I will save you the trouble of really rearranging the Schrödinger equation because from the potential study, you should be familiar with it already. Now, a few things I want to point out. Notice that now we have kept the two solutions e to the k2x and e to the minus k2x of the region when x is between 0 to a. Okay, we don't have this diverging solutions anymore, even though when x tends towards infinity, this solution would diverge, and then I talked about based on the context we can eliminate the solution. But notice now that x does not diverge to infinity in this region because x is bounded between 0 to a, so we must retain both solutions. Alright, now as long as the solutions are bounded, okay, we must retain them because for all we know, it could be bounded in this region over here, such as when x is equal to a, the solution doesn't go out of the potential barrier. So keep both solutions. The other thing I want to draw your attention to is that it must be a strict inequality over here. X is between 0 to a, and it cannot be equal from equal to 0 equal to a, because simple reason is that the potential barrier must have a finite width, okay? It cannot have 0. That's why implicit in this inequality is that a is greater than 0, so it's a strict inequality. And then k1 squared and k2 squared is given by this over here. So now for our preliminary examination, we want to sketch the probability densities of all these solutions over here, bearing in mind again that probability densities takes into account all the solutions, which is another reason why I left this part of the solution over here, because today's lesson is about sketching the probability densities. By sketching the probability densities, we at least get an idea of what's going on. Now I know that sometimes I say that sketching the probability densities are unphysical, but what is more important is that at least we know that if we sketch the probability density and it's an oscillating solution, even though it is unphysical, it tells us that the particle can actually be in that region wherever it may be oscillating. We can carry out the Fourier transform, but what's more important is that the probability density does not equal to 0 in that region over there. If it does not equal to 0, that means the probability of the particle existing in that region is actually more than 0. It can be found in that area. Okay, so let's sketch out the probability densities. Now for psi 1 and psi 3, it's quite easy. Okay, from psi 1 is equals to something over here plus, and I can rearrange it as I did many times before. What I did was that I write e to the ik1x and e to the minus ik1x as the cosine terms and the sine terms, and then I will take the magnitude. I'll get something like this, okay, if you just do the algebra, and same thing for psi 3 if you do the algebra. Both is a sine squared k1x, okay, both is a sine squared k1x, but what is different is really the coefficients in front of it. We see that this is a to a minus b squared minus a plus b squared, and this one is e and f over here. Okay, so what does this tell us? Well, this tells us first that since it's psi squared k1x, the k1x stays the same because as you can see in these two regions the potential is 0. That means that the period of the oscillation will be the same. Okay, do we understand that? Yes, we should. If it's the same argument of a same trigonometry function, the period is the same. But what is different is the amplitude. Okay, it's the amplitude of the oscillating solution. Now, this case is a minus b. Okay, but this case is e minus f. But by using the continuity conditions, which we would really use later on, we can actually say that this a minus b, okay, a minus b minus a plus b squared is actually more than e minus f squared plus e plus f squared. Okay, it's actually more than that. And because it's more than that, I can sketch it out immediately that this is gonna be oscillating more. Okay, it's gonna oscillating more, but as I enter the region for x greater than a, which is governed by the solution psi 3, and since psi 3 it has e minus f squared minus e plus f squared, and we know that this is less than this, the amplitude of the oscillating solution at x greater than a is actually, the amplitude is less, but it's oscillating with the same period. So if I were to sketch it out, it would be like that. Okay, should be like that. Okay, so immediately we can see that for some funny reason, by showing this equation, the wave function does not equal to 0 at this point over here. So it really kind of suggests to us that yes, the particle can exist in that region. Okay, but the story is not yet complete because we really don't know what happens inside here. Remember, there's this evanescent wave as we enter the potential barrier. So we really don't know what's inside here. But for us to find out what's inside here, we will now deal with the probability density function at x between 0 and a, okay, which is governed by psi 2. Okay, I hope you can see that. So psi 1 and psi 3, sketching the probability densities, magnitude of psi in terms of x squared, we will get these oscillating solutions because we managed to reduce the probability densities to sine functions. They're the same, period is the same, but amplitude is different. Okay, and we will know that if we will apply the continuity conditions, the amplitude, okay, is greater at the region x less than 0. Okay, x less than a is more. But let's see what happens from x between 0 to a, okay, where the solution is given by psi 2. So now I want to sketch the probability density of psi 2 and let's see what I get. Okay, so really we want to see how does the wave go from this to this. Okay, now probability density, magnitude of psi 2 squared, it can be written as the conjugate of psi 2 multiplied by psi 2 itself. Now let's do that for the solution over here. At least see what I get. Okay, so the magnitude of psi 2 squared is equals to c to the e k2x plus d e to the minus k2x. Now notice here that e is not raised to the power of I. So if I take the conjugate, they stay the same. However, I want to mention that since we are dealing in quantum mechanics, the constants, okay, c and d, which are actually the constants of the solutions to showing the equation, can be complex. So if I were to take the conjugate, I would need to take the conjugate of these two constants as well, which is what I'll do. Okay, I'll take the conjugate like that. And then now I will multiply by the psi 2 itself. Okay, so c e k2x plus d e minus k2x. Okay, notice again that it is a plus. Okay, now if there was I over here, it would be a minus, but since there's no I, it's a plus. And then when I do that, this is what I get. Okay, so I will just multiply this by this. So the conjugate of c multiplied by c itself is actually becomes the magnitude of c squared. Okay, e to the k2x, I'll multiply by itself is e to the minus k2x. Alright, and then I'll multiply this by this, noticing that the transcendent numbers cancel out because k2x plus minus k2x is 0, so e to the 0 is 1. So I would have with plus, okay, let's just open a bracket, okay, c conjugate multiplied by d plus, I got a d conjugate multiplied by c. The same thing happens here, and then I'll plus with a magnitude of d squared and e to the 2k2x. Alright, let's see whether is that correct. So this multiplied by this term is a minus. Okay, so this multiplied by this is minus k2x minus k2x is minus 2k2x, but is the magnitude of d squared. Okay, because d conjugate multiplied by d. So this is the probability density function. And if we want to sketch it out, my first question to you is, have you seen a function like that? Okay, chances are you have not. Okay, we need to make one small assumption. Let's just assume that this is a real number, okay, because we need to sketch a real function. So actually it turns out that if we use the continuity conditions, it's actually a real number. So let's just assume that that's a real number.